All right. We're going to talk about microscopes and telescopes today. Here's the image of the microscope that is in your textbook. We're going to work on a fairly simplified, a little bit simpler diagram than this. But before we do that, I want to do a small calculation with you in iClicker. So take your clicker out. And last time we talked about the thin lens approximation, and that is what your question is about. So type in a number and then hit the send key. And we're on frequency AB, so don't mess up. Now, do I take custody of these or do you? I'll take custody of them. Get them to Esperanza? Okay. Right, let's see if we can, oh, we can't seal it. Yeah, we'll get it to her. Can you take these to Esperanza up on the 4th floor in the main physics office?
The 4th floor of the physics?
Yeah, after class. I mean, when you're over there. Are you going to be over there today?
Why not? I have a whole hour to go after class.
430. All right, work out your equations. "45 seconds starting right now." All right, we're going to do document cams, so be ready to, move this and stuff right after this question. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you guys did good. 13.33 is the correct answer. Most of you got that. Let's go to the document cam now. We'll do some sketching. You don't have to do anything yet. This is just one page. We're going to do, switch me over to the document cam, please. Thank you. We're going to do a sketch today of a microscope, and I'll be using graph paper. And boy, if you haven't gotten any graph paper yet, you definitely want to try to do that. All right, so here's our setup. We're going to have two lenses, the objective lens and the eyepiece lens. Now, the focal length for the objective lens is going to be 5 blocks. And for the eyepiece lens, it's going to be 15. We're going to put the object distance at 8 blocks away from the objective lens. So it's going to be a little bit past the focal point. Now, the focal point on the other side of the objective is going to be separated by 2 blocks from the focal point of the eyepiece. So let's get this set up. Can you get me an emergency straight edge that's fairly long?
Unknown caller.
Can you give me my phone? Hello? Certain suspicious activities. I thought it was lift. Okay. So this will have to do. Okay, so here we go. All right, and I'm going to go horizontally with my graph papyrus. So, and we're going to pretty much need the entire page side to side. So if you're using notebook paper, here's my optic axis, and I'm just going to run it all the way across. If you're using notebook paper, you should be okay, but you're going to have to eyeball in your object distances and stuff. But hopefully it won't be too bodacious. All right, let's put, now let me go to pencil here. Okay, so there's my optic axis. Now I'm going to put my objective lens out here, and I'm going to make it 2 blocks tall, because I'm going to make my image or my object 1 block tall. Let me just label this as the objective lens. Okay, so there's my objective lens. Now, its focal points left and right are 5 units out. So here's one of them. And then 5 units to the right. All right, so there's the focal point on the other side of the lens. All right, now I'm going to put my object distance at 8 blocks. So that's another 3 blocks. So here's my object, and I'm going to make it pretty small today, because we're going to get a lot of magnification in the final image, and I don't want it to be too bodacious. So I'm going to start with 1 block, and then the number of vertical blocks that we get in our final image, Rashid Haroon, we're going to they'll indicate for us the total magnification. So we're starting small, 1 block, and we're going to get some additional magnification. Now, here's the focal point, the inner focal point of the objective lens. Now go 2 blocks to the right of that, and that's where we're going to put the focal length, and I'm going to put it up here, the focal point of the eyepiece. So here's the focal point of the objective lens, and here's the other one over here. I'm not going to label this one. Okay. So now, now 15 units from this point to the right is my eyepiece lens. So let me count out 3, 6, 9, 12, 15. So right here is my eyepiece lens. And I'm going to make that a little bit taller. I'm going to make it, let's see, what have I got here? 4 blocks tall. Now in reality, they're both going to be similar sizes, but just for, you know, for this kind of rough sketching business, we're going to need a little bit of. Okay, so there's my eyepiece. All right. Now we've got everything that we need to do our ray tracing now. All right. But we're going to have to do 2 different ray tracings, because the principle is that the image of this object, here's my object out here, point O, the image of that baby formed by the objective lens becomes the object of the eyepiece lens. So it's kind of like a chain reaction. So first thing we got to do is figure out the object or the image of this object in the objective lens. All right, now we know how to do that. So what I'm going to do is my first ray, as usual for me, my standard trick is drawing the ray that comes from the top of the object straight parallel to the axis into the lens. Right, so that's this ray here. Okay, and I'll put a little arrow to indicate that that's a ray. All right, now it refracts in the thin lens and it dips straight to this objective focal point. All right, so that's this one. And the thing about it is, it's going to keep on going to the eye. Oh, this is nice. I've got enough distance here to go all the way to the eyepiece. All right. And one thing I want to point out, this incoming ray here is 1 block high, and it's going to go to this block, to this focal point, which is 1 block down and 5 blocks over. So the slope of my line here is 5 to 1, or 1 over 5. The slope is, and it's actually negative 1/5. So let me go just to make sure this is down 1, 1, 2, 3, 4, 5. Okay, so it's going to go through this point, down 1, 1, 2, 3, 4, 5. Okay, so that gives me 3 points. I'm going to line up, and I'll make my line a little bit more precise. Okay, so here's your, okay, and we may have to run that out a little bit further, but that's your first ray. Okay, now my standard trick is to use the ray that goes through the center, through the symmetry point here, and let me label the symmetry point, S for symmetry, and it just keeps on going. Just goes cruising. Now this one is down 1, it's this line segment right here is down 1 over 8. So my next point on this line is down 1 and over 8. So 1, 2, 3, 4, 5, 6, 7, 8. All right, and you can see that when I draw this one in through this point, they're almost intersecting. So let me go down one more, down 1 over 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they're gonna, by the time it gets over here, they're gonna intersect. So I've got my second image in here. So let me, so my second image, let me make that a little bit longer. Okay, so we get an image right about here. Now let's check the image distance. It's supposed to be 13.3, right? So let's check. 2, 4, 6, 8, 10, 12, 13. Yeah, we're doing pretty good. That's about 13.3. So I'm going to put a dot right about here and let my ray tracing establish the fact that definitely I've got some magnification here, right? Because Melanie Rosario, it's down more than 1 block below the optic axis. So I've got, right now I've got a magnification of about 1.5. All right. So here's my image. Okay, and I'm going to call that position I1 because that's the image of, that's the location of the first image. Now, what we do next, Maria, we use that as the object for another ray tracing interaction in this lens over here. So what's my standard trick? Well, my usual standard trick is to go in parallel, but I don't have enough room to draw on the focal point. There's another focal point out here. So I don't have enough room, quite enough room for that. But I do have enough room for an object that seems to come from this focal point. If it comes from this focal point on this side, and slants down to this dot and then just keeps going, it's going to go through parallel. All right. It's going to come out on the other side parallel. So here, let me do it now. Okay. So from this focal point through the object, let me make this, all right, here we go. Now I'm going all the way to the lens. So from the focal point to the object, all the way through the lens. All right. So, right. Now that one goes through the lens parallel to the optic axis because it appears to come, now I'm not going to draw it in, but it appears to come from this one over here. Right, and I'll make a note of that over here. Let's see. Appears to come. It comes from this image, but it appears to come from I1. All right, it appears to come from FE. All right, and so it goes through the lens. Now you're over here on the far side of the lens eyeballing this. All right, so you're over here somewhere. All right, and it comes through parallel to the lens. So you're over here, put the letter U over here to indicate your eyeball. You're over there. So you see a ray that comes through in that direction. All right. So now back that up. We're going to get an image over here. And so we're going to back it up. So I'm going to do dotted lines here to back it up. This final outgoing ray here appears to come from this direction. So my final image is going to be somewhere along this horizontal dotted line here. All right. Now the other ray that I'm going to use is from the top of my secondary object, primary image, secondary object, right through the second symmetry point. So I'll call this S2. All right, the symmetry point of the eyepiece. Now this one's kind of cinchy, and it goes straight through. All right, now we know that. Okay, that's my usual second ray. All right, but it appears to come from way back here. All right, so go to the image and back it up now. It's not coming from here, but to your eyeball, it appears to come from here. Way back here. And this one, let me back this one up a little bit. So this is the location of your image, your final image. And let's call it's almost, in this sketch, it's almost, it looks about 4 blocks high, and so the magnification is about 4. And you can calculate it out using focal lengths and object distances and stuff. But this is how a microscope works. The key is to put a little bit of a gap right here. This is the key. This 2-block gap between the two focal points helps you have a real microscope in which you're over here to the far right over here, and you're eyeballing this. So your eye is about, so I'll sketch in your eye. So your eye is over here, and this is like this gigantic eye here. Okay, so you're eyeballing it, and it appears to be over here, which is at least 4 times bigger than the original object itself. So this is kind of a weak microscope. And fancy microscope, they'll go up to 1,000 power or more, but they're basically work in this principle. And they have reflectors and stuff that they can use, whatnot. But so this is a refracting microscope. Now this has nothing to do with an electron microscope. This is a little different. It's an optical microscope. All right. So the chain reaction is image in the objective becomes the object in the eyepiece. And then the eyepiece's image is what you see. All right, so here's kind of the chain of logic. The image in the objective lens becomes the object in the eyepiece lens, and then that's the thing that you actually see. All right. Now, a telescope, we don't need to, well, it's nice to magnify things with a telescope too. But the real power of a telescope is its light gathering power. Now, we're going to talk about telescopes in a second. So let me pause for questions about this diagram. Any questions? Yes.
Is clarity indicated by like how far the object is from the objective?
Clarity? No, clarity is not. Clarity, I mean, you can have muddy lenses here and they'll form an image. Now, it might not be a very good image, but that's what they'll form. What we've done is figure out the magnification and the location of the image. And it's inverted and it's real. You could put film there if you can. But the clarity just depends on the quality of the optics. You know, what kind of glass you're using, how pure is it? You know, how precisely controlled is it? And does it introduce aberrations, you know, like the spherical aberration we talked about the other day? And there's all kinds of chromatic aberration because different colors refract at slightly different angles. So when you have something going through a lens, now that doesn't happen with mirrors so much, but it does happen with lenses because lenses are refractive. Okay, so you get a little bit of a chromatic aberration due to that fact. And that's what clarity and resolution have to do with everything. But for just image location, this is basically it. Yeah, location and magnification. And this is ray tracing. You could do, you know, one of the things about this, you notice that I use you know, the rise over the run for making my sketches. And you can work with this all out geometrically and using, you know, y equals mx plus b and simultaneous equations and stuff. It's a lot of algebra, but you can do it. And computers, that's what computers do. You know, computers figure out exactly where it's going to go using those kind of techniques. Okay, switch me over to the laptop, please. Thank you. All right, so that's the microscope image on the dot cam. Now let's talk about telescopes and binoculars. And this is simple pair of lenses as well. And Galileo is famous for inventing the telescope, but he didn't really invent it. What he invented was using it to look at the heavens. And he just tilted it up and said, let me look at the moon. Let me look at Jupiter. And he found the moons of Jupiter. It's a huge revolutionary discovery. So again, you know, here's a telescope, a spyglass, you might call it. And the eyepiece and the objective are the same. And in this picture, you can see that it's kind of, you know, like if you look at that movie, Crouching Tiger, Hidden Dragon, Dark Cloud has a spyglass that he folds up. And what the folding up does, the telescoping, even that verb, telescoping, that's so that you can move the focal point, you know, the position of the lenses slightly and get into focus for your eye. So if you have bad eyes, you know, it might not focus well for you until you adjust it. Same with binoculars. All right, so here's a picture of a spyglass with a concave eyepiece and a convex objective. All right, and it gives you a final image, and you can see it's a big final image, pretty nice and big. But notice that the rays are coming in fairly parallel to the optic axis. Not exactly. And that's one of the factors of a telescope. The object distance is approaching infinity. All right, so that means that most of the rays come in very close to paraxial limit. All right, and especially parallel to the optic axis. So now here's a telescope like what Galileo was using, a couple convex lenses. And you can see it looks like the microscope picture. And it has an upside down, an upside down final image. And it's way over there. It's quite magnified. And so what we're going to do here, now notice that they have a gap between the eyepiece foci, the eyepiece focal point, and the objective focal point. But what I want to show you today is a very simple telescope diagram. All right. Can you switch me back to document cam? All right, so this is the microscope. And I'll put these in Instagram and so forth a little bit later. Now the telescope, go ahead and make your notes for this. Where's my protractor? Here it is. We're going to use the same two focal lengths. And for this one, I'm setting the object distance to be infinity. All right, so this is like looking at a star. That's basically, you know, so many zillion times bigger than the focal length that you just say it's infinity. But the separation between the focal points for this telescope is going to be zip zap. All right. So let me draw an optic axis. We're going to draw the same optic axis, matter of fact. And this one's going to be a little bit simpler. We're not going to do it. We're not going to do an image. We're just going to draw some parallel rays coming in from a star. Or in reality, you know, any if you have a camera lens, anything greater than about 20 feet is effectively infinity. All right, so here's my optic axis, and let's put in a dot here for my eyepiece lens. Now, what we're going to do with the eyepiece is make it pretty big. Or excuse me, the objective. I'm going to make it 4 blocks high. Okay, so there's the objective lens, and this is point S. And it's 5 blocks over here, and then 5 blocks over here. Okay. Now so this is, let's just label this point F. That's going to be the common focal point. And this is the focal point of the objective lens out here. Now that's also the focal point of my eyepiece lens. So let's put the eyepiece lens 15 blocks to the right of that. Okay, 2, 4, 6, 8, 10, 12, 14, 15. Okay, so right here. And let's make this one 2 blocks tall. It's an eyepiece on a telescope, so it's going to be a little bit bigger or a little bit smaller. All right, so there's my eyepiece. All right, now this one's going to be a little cinchier. Let me get my red ink pen. Where's my, Andrew, can you give me my pencil case over there? Thank you. Where's my, here it is. Okay. All right, first thing we're going to do is draw in a ray one unit high, parallel to the optic axis. There we go. Now that's going to go through this focal point, and it's going to go all the way out to the eyepiece. Now the eyepiece is a little bit small, but we can still run it out a little bit further. Okay. And now it interacts with the eyepiece and it goes straight out parallel because it came from the eyepiece focal point. So here's one of your rays. So here's your star out here that you're looking at. All right. So Alpha Centauri or whatever star you're looking at is out here. So the light rays pretty much come in parallel. And then they go into the eyepiece. And then the same thing, let's go to a light ray coming in one block down. Through the focal point, the common focal point, and all the way out to the eyepiece, and then from the eyepiece parallel to the optic axis. Okay, so that's right about here. Okay. So here's the scoop. So this is your eyepiece. If your objective lens is greater than your eyepiece, so think binoculars. Okay, the front end of a binoculars, maybe a couple 3 inches, and then the eyepiece is basically at like a half an inch. So if the objective lens is bigger than the eyepiece, all of the light into the front end of the telescope, i.e. the objective, gets concentrated in the eyepiece. So the image, the main thing, even if you don't get a lot of magnification, the image is brighter. And so you can see really dim stars, etc. Okay, and that's how we use telescopes. Now, I'll just make a note to you that in my annotations, I make a reference to the Hubble Space Telescope. And the Hubble Space Telescope is basically our attempt to have a 2.4 meter mirror. So Hubble Space Telescope's not lenses, it's a mirror, but same philosophy. The light gathering power is like 90,000 times more than the human eye. And that is significant. So you can see very dim objects with the Hubble, and everybody's seen pictures from Hubble. They're fantastic. And we take time exposure. Sometimes it takes time. They need a lot of shots at the same object to get a good fill in of color and detail and stuff. But yeah, go ahead and read the annotations on Hubble in chapter. I think it's in chapter 26 on telescopes. Right, so that's our main lesson for telescopes. And you know, the whole idea of microscopes is very similar. All right, just slightly different arrangement of the optics, you know, the focal lengths and that kind of stuff. But basically, the advantage for a telescope is it's you know, you want it, Krishna, you want it to be clear. You want really good glass, but the real thing is you want more light. Oh, you know what else? Let me make a caution to you. Do not view the full moon through a telescope or even binoculars. You know, it's okay to look at like a crescent moon. Crescent moon is okay. But anything more than a crescent moon, you're going to burn your retinas. You can burn your retinas out. And you know who was the first guy to do that? Galileo. He was looking at sunspots. And, you know, good going, Galileo. And he went blind in his later days. So it's, you know, so don't do that. So even the moon can burn your eyes out. You don't want to do that. So that's my admonition to you. Do not burn your eyeballs out. I'm sorry I have to go through that, but since you guys are newbies at telescopes and stuff, yeah, we have to go over some of the basic specs about burning your eyes out. Okay. You want to switch me back to the laptop? Thank you. All right, let's keep going. Here's another set of diagrams, and this is from Brand X, another textbook. I'm not going to mention their name. And this shows you, you know, the eyepiece and objective. There's your distant object, and you can see the second image. It basically, you know, there's the second drawing. The final image is quite a bit bigger. So here's the thing about it. You know, you have proportional triangles all over the place. So like this one here, they've got that break, you know, the squiggles to indicate a break, but it's basically proportional to this one down here. So you can work out all this stuff. You can work out these positions pretty nicely under the thin lens approximation. All right. You know, I see a lot of people not looking at these diagrams. My God, you know, if I'm talking about a damn diagram, you better be looking at it. I still don't see people looking at the diagram. You know, God bless you. I try, but you know. All right, so here's the second focal length, the eyepiece image, right? Um, and then, you know, here's another set of proportional triangles. Now, this is different from the first set, right? But that one, and then this big triangle out here, they're actually nested together. So proportional right triangles. Now, here's this idea that I mentioned, you know, that you have a chain of foci. And this is just simply one way of computing and handling a telescope observation. All right, so you have your objective lens, and the focal length of your objective is marked in two different places, F subscript object and then F regular. And then the eyepiece, you put it in place so that the eyepiece focal point is at the same point F as the objective lens's focal point. All right, so that's what we did in the previous diagram. All right, so you basically have a chain of foci, and therefore you have a bunch of proportional right triangles that you can work with. So it's like a chain of computation. And so here's your eye out here, and you're getting stuff like this. It comes in parallel. It dips through the focal point, common focal point, hits the eyepiece, and then comes out to your eyeball. All right. And this diagram, I made it so that the the objective lens is larger and focusing nicely into the eyepiece. So this one shows that you have a lot more light gathering power. You know what this is like? This is like a pair of binoculars. You know, between the objective lens, the aperture or the size of the two lenses. You know, the objective is a little bit bigger on a binocular than the eyepiece. And so this emphasizes the light gathering power of binoculars or telescopes. Now, let me ask you a question. Why does your eye prefer parallel rays incoming? And that's another feature of where you put the eyepiece. You want those rays coming out parallel to the optic axis or as close as you can. All right, so hit the refresh key and let's do a multiple choice question with your eye clicker. And if you've done any reading as you were supposed to be doing, you'll know the answer to this. So let me switch over to multiple choice and answer this question. Why does your eye prefer parallel rays incoming? Okay, go ahead and start. "30 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, the answer to this one is here, and most of you got that. Very good. So this is a picture of the eyeball, and if you've had what do you call it, anatomy class, you probably looked at diagrams like this. I don't know what's in anatomy class. I don't want to know what's in anatomy class. But let's talk about eyeballs a little bit. It's kind of a complex system. You have the lens, and then you have the aqueous humor. And the aqueous humor is aqueous, so it's about it's about the same index of refraction as water. And then the cornea is about 1.38, and the lens itself is about 1.40. So it's a little bit faster than a glass. You know, glass is about 1.5, and of course, air is outside of everything, 1.000293. So you have different refractions going on, and the other thing that you have is it's adaptive optics, in that the muscles that attach to the lens can change its size and shape so that you get good images on the retina at the back of the eye. You know, then they fire the optic nerve, and then your brain processes. All right, so here's the relaxed lens. Those muscles are not pulling very hard, or I should say they're not pulling the lens. The second image is a tensed lens, and it changes the focal length just a little bit so that you get another thing to focus on the lens or on the retina. All right, so that's why when you have, you know, like for me, my specs, I don't know about you guys, but I only need them for reading pretty much. Okay, so like, you know, if I put these on, the display over there is kind of fuzzy. All right, because it's way too. Now, when I take them off, I can see the display just sharp as a tack. All right, but reading up close is what I need, so that's why I have these cheaters. All right, and so everybody that has glasses, you're trying to get something to where your eye can do this, or that your glasses can help your eye do this a little bit better. All right, so so here's the relax. Here's a close up. And these little muscles down there, those little gray blobs above and below the lens, yeah, they're the ones that control that. They control the shape of the lens, and therefore the refraction is going to change a little bit. So, and they have a nice little few pages about the eyeball you can read about in the textbook if you're interested in that kind of stuff. Now, I want to talk about our next topic in chapter 27 now, which is interference. And this is something that we saw. This is the discrete spectrum of helium with the quantum fingerprints of helium, specifically that big yellowy one there that's very prominent. See, it's got a good red line over there, but so does hydrogen. But hydrogen doesn't have that yellowy line at all. So you can distinguish between different things. Now, this is just a little bit of a review about interference of waves in general. If you have two sources of waves and the waves move out independently, at certain points in your medium, like if you're out in the ocean, you're going to have two wave crests meeting. And where they do, you're going to have a super big rogue wave. Or if it's at the beach, you're going to have a nice big surf, nice big piece of chunk of surf coming in. All right. At other points, you might get two troughs. Now, when that happens, you get a really deep part of the ocean. I would consider it frightening to be in a ship where a rogue wave hits. First, you get the wall of water coming at you, and then you float over the top of that, hopefully. And then on the other side, you're looking down into this extra deep trough, all the way down to Davy Jones' locker. Oh my goodness, that would be like a nightmare for me. But anyway, so all that stuff is called constructive interference. The waves add together. And go ahead and make a note. For us, the waves are in phase, or the phases match from the two sources. So you're talking pi over 2 meeting pi over 2 for a rogue wave, and 3 pi over 2 meeting 3 pi over 2 for an extra deep trough, a doubly deep trough. And where pi over 2 meets pi, you get a little bit of something. All right. And when pi over 2 meets 3 pi over 2, you get zip zap. And that's called a crest and a trough together. You get no wave. That's what we call destructive interference. Now, I don't know if you guys learned this in 2053, but my students did. All right. And you can read about it in some of the other earlier chapters in our free textbook. Now, here's a picture, kind of an idealized picture of two waves interacting, wave A and wave B. So one of them's, like coming in from a storm off the coast of West Africa, and the other one's coming in from a storm off the coast of Nova Scotia, and they meet somewhere out in the Atlantic, out, 1,000 miles from Bermuda or wherever they meet. And where they do, they form a really big wave. And the shapes are about the same. So it adds up to a shape, pretty much the same shape, but twice as high, A plus B. The waves add together. All right. And that's because they have equal phases. You don't have, in this one, you don't have a dip in the wave. You just have a bump. And there's waves that do that. All right. So this is kind of simplified. Now, this is at the point where they interact. Now, what happens after that? Do they bounce off each other? No, they do not. They keep going on their merry way. So wave B that started off the coast of West Africa, it keeps heading for Nova Scotia. And wave A that started in Nova Scotia, it keeps heading on down towards the coast of West Africa, at their original amplitude. Now, eventually waves will wear out and they'll dissipate energy and stuff, but this is kind of an idealized view. Now, here's where opposite phases interact. You'll get zero amplitude. This is destructive interference. So this is a bump coming up from the coast of West Africa, and a dip coming up from the coast of West Africa, and a bump coming in from Nova Scotia. All right, now they're out of phase. You get flat water or zero amplitude. Now here's the thing. In real waves, a real train of waves from storms at sea, you're getting bumps and dips. You bob up and down. If you're out there in the water, you're in a boat, you're going up and down, above sea level, below sea level, above sea level, below sea level. It oscillates. And so you get a combination of these. So what you really get out in the middle of the ocean is a combination of rogue waves, doubly deep troughs, and in between them, flat water. Now, it's not a lot of flat water, but it is. And it's flat, all right? It's still going to be pretty scary if you ask me. But and it varies with time. So one point in time, at a certain location, it's going to oscillate between destructive and constructive interference, all right? Depending on the position of the source, all right? So here's the flat water, and after the interaction, the waves, as before, they keep going off along their merry way, all right? And just a side note to you, this is a one-dimensional wave picture. All right. Now we're not going to do a whole lot with this. We did some stuff with this in 2053. But another one I want to go through with you is relative to our class, and that's radar guns. The radar guns that the cops use to bag speeders is based on this idea of beats. All right. Now, beats happens when you have two wave sources at slightly different frequencies. All right, so F1 and F2 up there, you can see that over here on the left of this diagram, the phases match pretty good over here. So you get a big rogue wave. Now over here in the middle of the diagram, the phases are 180 degrees out of phase, right? They're opposite. So that's a trough meeting a bump. And when that happens, you get zip zap. Now they put a little bit of squiggliness here because the pictures aren't exact. But then, a little bit further down the line, you get constructive interference. Now, my wonderful students, the distance from this peak here of constructive interference to the next peak, that's the wavelength of the beats, all right? So if you're out there in the ocean, you're not going to see the waves coming in at their normal frequency. You'll see them coming in at a slightly, you'll see beats separated by a bigger wavelength and a smaller frequency. Now, here's a really good diagram. Question? Good? Now, I made this diagram. The other one's from a Brand X textbook. It's nice, but this is precise. All right, so here's two wavelengths, different frequencies and wavelengths. And go ahead and make a note. The beat frequency, F subscript B, is simply the difference between the two frequencies. So if you have two sources, the black source and the red source, and they're slightly different wavelengths and stuff, you'll get beats. Now look at these. Over here on the left side, the phases are pretty close. But by the time you get down here towards the middle, you're looking at a peak of the black wave opposite a trough of the red wave. So they're just a little bit out of phase. Actually, they're quite a bit out of phase there. So, okay, hold on, I have to do something here. All right, so let's take a look at the numbers for this. I cranked out. So this is like sea level. The equilibrium line is like sea level. So you can think of these as sea waves, but for our class, we're going to think of it as electromagnetic waves. All right, and I'm doing a phony speed, 80 meters per second. If it was really electromagnetic waves, it'd be 3 times 10 to the 8 meters per second. Okay, so I just made this is kind of a make-believe system. But I set up the frequency number one to be 106.7 and the other one to be 119.5. All right. Now from that, and knowing the speed, you can figure out the wavelengths, and you can see that they have different wavelengths. If F1 and F2 are different, lambda 1 and lambda 2 are going to be different. And we're going to diagram that in a second. The beat frequency is simply the difference. Now, when you add both of these signals, these electric fields together, like in a circuit or something, this is what you get. This is an exact diagram, all right? So here's your maximum here on the left. Here's your flat water situation here towards the middle. And you can see that the black and the red above that are approximately opposite in phase. Okay, so that's your flat water. And then you come to another maximum over here to the right. All right, and this is the sum of the black and the red. All right, so you could do that in a circuit. Just put them both into the same circuit and, measure your amplitudes and whatnot. All right, now, this is if this was audio signals coming out of two different speakers, this is what you'd hear. All right, you'd hear I wish I had brought the beats demonstration here, but you can hear it audio. There's audible beats. So, and raise your hand if you play guitar. Anybody here play guitar? One person. Raise your hand high. Let me see. Okay. If you play guitar, have you ever played guitar with somebody that their guitar's out of tune?
Yeah, it's really annoying.
You get a buzzing sound. I mean, if you were to listen to the recording, you'd hear a buzzing sound, and that's beats. Because they're not. If you're on and they're slightly off, it sounds terrible. All right. So this over here, large amplitude. This is your loud. And then right here, flat water. That's where this faint. And then here it is loud again over here. So this distance, the frequency is 12.8. That's the difference. And this distance here, lambda beats 6.25 meters. That's this one right here. Go ahead and pencil that one in. Hold on. All right. Now, this is what we've just gone through is a very, very simple description of what waves do. To get to the fancy stuff like diffraction, we have to introduce this principle, Huygens principle. It's all about wavelets. At every point on a wavefront, the medium acts as if it's a source. This is, we have two, I have to, hold on a second, you guys. Let me pause this. I have to do something. This is embarrassing. How annoying. All right, let's keep going. So diffraction is an area where we have to apply Huygens principle. So what happens is every point in the medium is like a source of circular waves. And this diagram shows kind of what we mean by that. Between these two gaps in the barrier, so here's a wall, a doorway and a wall, and this is using sound waves. But electromagnetic waves, we think, work the same way. So there's a gap, a door on the wall, and it's open. And what we think is that the waves propagate through the door as if they're have many sources right here. And so those wavelets coming out here, these little circular jobs, they constructively interfere and form a blue wavefront that has this shape right here, right? And when that happens, as you can see, the sound waves will diffract around the edge of the door, right? So Huygens principle, every point on a wavefront acts as a source of tiny wavelets that move forward with the same speed as the wave. The wavefront at a later instant is the surface that is tangent to the wavelets. And that's that second thick blue line, the curved blue line here, all right? And this one shows the effect for diffraction of sound waves. Here's ocean waves going through a gap. Here's another one from space. You can see big swells in the ocean going past these small islands. This is in the Indian Ocean, I believe. You know, this is a complicated situation, but you can see the waves changing directions in this diagram. Now, let's apply that to a fairly simple object, a baseball. So let's go ahead and make a sketch. And we're going to represent plane waves coming in from a distant source, shining on a baseball. So that could be like a spotlight 100 feet away. That's pretty much plane waves by the time it gets to the baseball. And the direction of propagation is toward the baseball. And the question is, what do you get on the back side of the baseball? All right. So here's what would normally happen for a baseball with visible light. You'll get a shadow. Now, a baseball is so big. Ah, hello. Yeah, it's supposed to be somebody named Rosie. All right, they're on the way. All right. Yeah, I've been trying to send you text messages. Just be patient; they'll be there. All right. And I told her your name is RJ. Okay, that it's not me, it's you getting a pickup. Okay. All right. God bless you. Sorry about that. I had to get I have the car, so I had to get a lift for my son for an appointment. It's in the middle of class, so you're seeing Dr. B at about his most embarrassed. Only one time worse, but I'm not going to go over that time with you. I was more embarrassed than this. Anyway, so here's the key. Now, if you're reading in the next chapter 27, you'll see my annotations. The key in all of this is the size of the wavelength relative to the size of the object past which the waves are trying to go. Now, if you have visible light, wavelengths are a few hundred nanometers. That's way smaller than a baseball. So those waves go blazing through there. They don't even think about the baseball at all. The diffraction effects are so small, it looks just like a straight shadow. Just like an eclipse of the sun. And if these are plane waves, so you're going to get a straight ahead shadow. Now, if you put a ball bearing there, ball bearing about, maybe a centimeter or maybe a half a centimeter in diameter, yeah, you can measure the diffraction around the edges. And here's what it looks like. So here are the Huygens wavelets cutting in. So go ahead and this is a ball bearing now. So now the ball bearing is small enough, if you do a really good job with a big wavelength of light like red, you can get some Huygens wavelets and visible diffraction. Now, what's going to happen? You're behind that ball bearing. That's supposed to be a shadow. But instead, what you get is a bright dot right there, right in the middle. In the middle of where it's supposed to be a shadow, you get a dot. Now, there's a famous story about this. In the 1800s or 1700s, maybe late 1700s, early 1800s, everybody was talking about, well, is light really a wave, or is it a particle? You know, particles behave like ray optics. Waves behave like this: diffraction optics, physical optics. And over there in Paris, France, they were saying, well, no, you're crazy. It's not waves. Just look at the evidence. And there's plenty of evidence for ray optics, shadows. And so one of the guys said, in fact, waves are so out of town, it can't possibly be waves. He said, look, if there were really waves, smart guy, you would get a dot behind an object like this, a small object. He said, you're not getting, it's a shadow back there. So you're out of town. And I think the guy that said that was named Poisson. And he said, forget it, you jokers. You're going to get some dot back there. But guess what? Somebody observed it. They set up an example. They set up really precise, and they took a photograph of it. Poisson's dot. And that sealed the fate of all the naysayers that said light was not a wave. This experiment proved it. And other experiments proved it. And they couldn't do anything about this one. They couldn't wiggle their way out of this one. Now, here's a diagram. This is from the Educational Development Center. I don't know where that is, but it shows the difference between diffraction effects for different wavelengths. All right. In the first image on the left, the wavelength is pretty small. In the image on the right, the wavelength is pretty big, roughly the same size as the opening. Now you can see the opening in the second image. And they made a really big opening in the first image. So those things, they just march through like soldiers, just going straight on through. Now you can see a little bit of diffraction. See that in the first image? But most of it, the energy just goes marching straight through, right? But if you have something that is about the same size as your wavelength, a gap or an obstacle, then you're going to get Poisson's spot. You're going to get diffraction. You're going to get some kind of interference like this. All right. Now, your homework for tonight is to read chapter 27 and read as much as you can, especially my annotations. And we're going to talk more about it on Wednesday. All right. You're dismissed.